right. So the crux in reinforcement learning is that the agent is going to, there is this learning agent, right, it's going to learn in a close interaction with an environment, right. So the environment could be the helicopter, it could be the cycle, right, and or it could be your backgammon board and your opponent. All of this could constitute the environment, a variety of different choices. So you sense the state in which the environment is in, right, you sense the state of the environment, okay, and figure out what is the action that you should take in response to the state, right. So you apply the action back to the environment, this causes a change in the state, right. So now comes the tricky part, right. So you should not just choose actions that are beneficial in the current state, but you should choose actions in such a way that they will put you in a state which is beneficial for you in the future, right. Just capturing the queen of your opponent is not enough in chess, right? That might give you a high reward, but it might put you in a really bad position. So you don't want that, right. You really want to be looking at the entire sequence of decisions that you are going to have to make, and then try to behave optimally with respect to that, right. So what we mean by behave optimally in this case, right, we are going to assume that the environment, right, is giving you some kind of an evaluation. It's like falling down hurts, right, or capturing a piece maybe gives you a small plus 0.5, or winning the game gives you like 100, right. So every time you win, every time you make a move, or every time you execute an action, you did not get a reward, or you did not get an evaluation from the environment, right. So it could be just zero, it could be nothing, right? So I should point out that this whole idea of having an evaluation come from the environment is just a mathematical convenience that we have here. But in reality, if you think about biological systems that are learning using reinforcement learning, right, all they are getting is their usual sensory inputs, right. So there is some fraction in the brain, okay, that sits there and interprets some of those sensory input as rewards or punishments, right. So you fall down, you get hurt, I mean that's still a sensory input that is coming from your skin, right. Or somebody pats you on the back, that's still a sensory input that comes from the skin, right. It's just another kind of an input, right. So you could choose to interpret this as a reward, right, or this as a collision with an obstacle, right. If something is brushing against my shoulder, let me move away, right, or you can just take it as somebody is patting my back, so I did something good, right. So it's a matter of interpretation. So this is this whole thing about having a state signal and having a separate evaluation coming from the environment is a fiction, right, that is created to have a cleaner mathematical model, but in reality things are a lot messier, you don't have such a clean separation, right. And like I said, so you have a stochastic environment, you have delayed evaluation, noisy. So the new term that we have added here is scalar. The new term we have added here is scalar. So that is one of the things with the classical reinforcement learning approaches. He said I am going to assume that my reward is a scalar signal, right. So we talked about getting hurt and having food and so on and so forth. What all of this will happen mathematically is I will convert that into some kind of a number on a scale, right. So getting hurt might be minus 100, right. Getting food might be plus 5, winning the game might be plus 20, right. Capturing a piece might be plus 0.5 or something like that. So I am going to convert them to a scale, right. And the goal is now that I have a single number that represents the evaluation, the goal is now to get as much as possible of that quantity over the long run. Okay, make sense? Right. So if you have questions, doubts, stop me and ask. So mathematically a scalar is easier to optimize. Not necessarily, right. I am just talking about, so it's like a cost function if you want to think about it in terms of control systems, right. So this is like a cost and I am trying to optimize the cost, right. And so if the cost is going to be vector valued, then I will have to start trading off one direction of the vector against the other. So which component of the vector is more important? So then you get into all kinds of so Pareto optimality kind of questions, and so it's not really clear what exactly is optimal in such cases. So here again let me emphasize, it's not supervised learning, right. In supervised learning this is essentially what you are going to see. There will be an input and there will be an output that you are producing, and somebody will be giving you a target output. Okay, so this is what you are supposed to produce, and essentially you compare the output you are producing to the target output, right, and you can form some error signal, right, and you can use that error in order to train your agent. Right, you can try to minimize the error, you can do gradient descent on the error, or you can do a variety of things, and you can try to train the agent. So here I don't have a target. I do have to learn a mapping from the input to the output, but I don't have a target, and hence I can't form an error, right, and therefore my trial and error becomes very essential. So if I have errors, right, I can form gradients of the errors, and I can go in the opposite direction of the gradient of the error, right, and then that gives me some direction in which to change my parameters, right, that constitute the agent. Right, my agent is going to be described in some way, right, the error gives me a direction, right, but now since I don't know a direction, right, so I do something, I get one evaluation, so I don't know whether the evaluation is good or bad, right. So think of writing an exam, right, I don't tell you the right answer, I just tell you 3, right, and so what do you do now? Are you happy with the answer? Should you change it? Should you change it in one direction, or should you change it in the other direction? See, what makes it even more tricky is you don't even know how much the exam is out of. So when I say 3, it could be 3 out of 3, right? It could be 3 out of 100, right? So it could be any of these things, right? So you don't even know whether 3 is a good number or a bad number. So you have to explore to figure out whether you can get higher than 3, right? Or 3 is the best. The second thing is, okay, if I can get higher than 3, how should I change my parameters to become higher than 3? Right, so I have to change my parameters a little bit that way. Okay, I have to change the parameters a little bit this way, right? So if I'm cycling, right, I have to push down a little harder on the pedal, okay, or I have to push down a little softer on the pedal to figure out whether I'm staying balanced for a longer period of time or not. Right, so I don't know that, otherwise unless I try these things I wouldn't know. This is why the trial and error part. So if I push down a little harder and I stay balanced, maybe I should try pushing down even more harder next time, right? So maybe that will make it better, right? And then there might be some point where I tip over, so I need to come back. So this is some things which you have to try. Unless you try that, you don't even know which direction you have to move in, right? So this is much more than just the psychological aspects of trial and error. There is also a mathematical reason. If you want to adapt my parameters, right, I need to know the gradient. Okay, so that you need to do this. Okay. Yeah. The reward is the one that that gives you the evaluation for the output, right. So here in the supervised case, the error is the evaluation for the output. If the error is 0, then your output is perfect, right. But then you have a way of gauging what the error is, because you have a target to which you can compare, right, and from there you get the error. So in the reinforcement learning case, the evaluation is directly given to you as the evaluation of the output, right. It is not necessarily comparing against a target value or anything. You don't know how the evaluation was generated, right. You just get an evaluation directly. So you just get some number corresponding to the output, right. So maybe I should have put an arrow from the top saying evaluation comes in from there, but that's exactly where it's coming. It's a substitute for the error signal, but it's just that you don't know what the evaluation is. Of course, the way it differs from the error is minor differences. You typically tend to minimize error, but you tend to maximize evaluation, right. It's also not unsupervised learning. So unsupervised learning has some kind of an input, right, that goes to the agent, and then it figures out what are the patterns in the input, right. Here you have some kind of an evaluation, and you are expected to produce an action in response to the input. It is not simply pattern detection, right. So you might want to detect patterns in the input so that you know what is the right response to give, but that is not the primary goal, right. But in unsupervised learning, the pattern detection itself is the primary goal. So that is the difference, right. So here is this one slide which I think is kind of the soul of reinforcement learning, right. It's called temporal difference. So I'll explain it a little more detail in a couple of slides, but the intuition here, right. So if you remember the Pavlov's dog experiment, right, what was the dog doing? It was predicting the outcome of the bell. If the bell rings, there is an outcome that's going to happen. It's predicting the outcome, which is food, is going to happen, and then it was reacting appropriate to the outcome, right. So most of reinforcement learning, you're going to be predicting some kind of outcome that's going to happen. See, am I going to get a reward if I do this, or am I going to not get a reward? Right? Am I going to win this game if I make this move, or am I not going to win this game? Right? So I'm always trying to predict the outcome. Right? The outcome here is the amount of reward or punishment I'm going to get. Right? This is essentially what I'm trying to predict at every point. Right? So the intuition behind what is called temporal difference learning is the following. Right? So the prediction that I make at time t plus 1, okay, of what will be the eventual outcome. Let us say I'm playing a game, right? I'm going to say, okay, I'm going to win now. Okay, I'm very sure I'm going to win now, right? So I can say that with a greater confidence when I'm closer to the end of the game than I can at the beginning of the game, right? So I have all the pieces set up, right? If I'm going to sit there then and say I'm going to win the game, right? It's most probably wishful thinking, right? But then you have played the game for like 30 minutes or something, and there are like 5 pieces left on the board. Now I'm going to say I'm going to win the game. Now I say I'm going to win the game. Right? That's a much more confident prediction than what I did at the beginning, right? So taking this to the extreme, right? So the prediction I make at t plus 1 is probably more accurate than the prediction I make at t. Correct? The prediction I make at t plus 1 is more accurate than the prediction I make at t. So if I want to improve the prediction I make at t, what can I do? I can go forward in time, right, and basically go to the next, let the clock tick over and see what is the prediction I will make at time t plus 1 with the additional knowledge I am getting. Right? I would have moved one step closer to the end of the game. So I know a little bit better about the game, right? I know how the game is proceeding. I know I can now make a prediction about whether I will win or lose, right? And use this, go back and modify the prediction I make at time t. Right? At t, I think there is a possibility of, say, probability of 0.6 of me winning the game. Okay, and then I make a move. Then I find out that I am going to lose the game with a very high probability. Then what will I do is I will go back and reduce the probability of winning that I made at time t. So instead of 0.6, I will say, okay, maybe 0.55 or something. Right? So next time I come to the same state as I was at time t, I won't make the prediction of 0.6, I will say 0.55. Right? That's essentially the idea behind temporal difference learning. Right? So it has a whole lot of advantages. We'll talk about it a couple of slides down. But one thing is it's had a significant impact in behavioral psychology and in neuroscience. Right? So it's widely accepted that animals actually use some form of temporal difference learning, and in fact there are specific models, right, that have been proposed for temporal difference learning, which seem to explain some of the neurotransmitter behaviors in the brain. Yeah.
So suppose we are playing a game and we have 10 moves that we can make, and out of 10 we will select the best one. Okay, this is the usual scenario.
Yeah.
So here the temporal difference is like we are selecting the move from next to next move.
No. See, at this point, I'll be making a prediction about what is the probability of winning. And it could be for each of the moves. Right? If I make this move, what is the probability of winning? If I make this move, what is the probability of winning? Let us say I make move 2. Okay. And then I see a new position, right? My opponent responds to it. And then I decide, oh my god, this is a much worse move than I thought earlier. So what I'll do is, I'll change the prediction I make for move 2 in the previous state. You see that the other moves will not be affected because the only move I took was 2. Only about that move I have additional information. Therefore, I can go back and change the prediction I make for move 2 alone. Okay. So you could still have the 10 moves. So you're not changing any of that. Yeah.
So are we going back and like changing the entire thing again, or just changing the prediction?
Changing the prediction. It's not like, I mean, in an ideal world, you should be able to take back a bad move. Right? Except if it's a parent playing with the kid, I don't think those things are allowed. Right? In fact, when I play with my son, we have sometimes had to rewind back all the way to the beginning. It will probably be me asking to do the rewinding, not him, because he'll be drubbing me in one of those games. But yeah, otherwise you can't. You just change the prediction. So next time you play the game, you will be better at it. At not for that game, well, basically you're messed up. Or you did well, I mean, so whatever it is. Yeah. Okay, I hope I was not too boring and somebody fell over or no. Right? Okay. Well, that is known to happen. Yeah. So people sleep, and I've actually had a person sleep and then fall off the chair once. Yeah, I still can't get over this. Okay, there is one time I was going to teach a class, right? And as I was entering the class, one person was leaving the class. I said, "Hey, what are you doing? You're supposed to be in my class." He said, "No, I feel very sleepy. I can't." I said, "I don't care if you're going to sleep. Just get back into the class, right?" And he looked at me for a minute. He just shrugged. He said, "Okay." And then he walked into the class, went to the last bench, actually lied down on the bench and went to sleep. Okay. And he recently sent me a friend request. Okay, going back to looking at RL, right? So let's look at tic-tac-toe. Right? How many of you have played tic-tac-toe? Good. Oh, even you put your hand up. Okay, good. Okay, good. So in tic-tac-toe, so you have these board positions, right? And so you make different moves. So in the first, this is what I have drawn here is called a game tree, right? So I start off with the initial board, which is empty, right? And there are how many possible branches there? For people making moves, 9 possible branches, right? For excess move, there are 9 possible moves. So I have 9 possible branches, and then for each of these, I'll have like 8 possible. I'm not sure which is the right TV. For each of these, I have 8 possible branches, and they keep going, right? So what we are going to be doing is essentially trying to let's formulate this as a reinforcement learning problem. So how will you do this as a reinforcement learning problem? Right? So I have all these board positions, right? Let us say X is the reinforcement learning agent and O is the opponent, right? So initially given a blank board, I'll have to choose one among 9 actions, right? So the state that I'm going to see is this blank, the X's and O's on the board, right? And the moves I'll be making are the actions, right? So in the initial position, I have 9 actions, I make that. Do I get any reward? Not really, there's no natural reward signal that you can give. Essentially the reward that I'm going to get in this case is, if at the end of the moves, if I win, I'll get a 1. If I don't win, I get a 0. Right? If I win, I get a 1. If I don't win, I get a 0. Right? So what is going to happen is, I'm going to keep playing these games multiple times, right? And at each point, right? Yeah, okay, so there is a note here. So what does that note say? You have to assume it's an imperfect opponent, right? Otherwise there's no point in trying to learn tic-tac-toe. Why? You'll always draw. And the way we have set up the game, you're indifferent between drawing and losing. So you learn nothing, I mean, basically. So you will not even learn to draw, okay? You'll just learn to nothing. Basically, you learn nothing because you can never win, right? So you're never going to get a reward of 1. So you'll just be playing randomly. So it's a bad idea. So let's assume that you have an agent that is imperfect, right? That makes mistakes, so that you can actually learn to figure out where the agent makes mistakes, where the opponent makes mistakes, and learn to exploit those things, okay? Right? So your states are going to be these board positions, as you can see, give you a game that is being played out on the top of the slide, right? And the actions you take are in response to those board positions. And finally, at the end of the game, right, if you win, you get a 1. If you don't win, you get a 0, right?
Sir.
Is it clear?
Sir, in cases like this, I mean, does it have to be a binary sort of a reward system? I mean, could you have a scale where there are 3 parameters? If you lose, it's 0. If you draw, it's 0.5. If you win, it's 1.
Sure. You could even do other things like if you win, it is 1. If you lose, it's -1.
So then couldn't you have a perfect opponent and learn?
Yeah, you possibly could, but you probably have to play a lot of games, because the perfect opponent, it's almost impossible for you to start getting any feedback in the beginning, right? You'll always be losing, so it's going to be hard for you to learn, but you'll eventually learn something. Yeah, it'll take a lot of moves, you'll eventually learn something. Go back. So if I say that at every point,
when we are learning, like at a particular stage, the probabilities of winning and when you update a previous state, so you're storing information for each and every state that you have entered, right? So how will it be different from exploring the like state space every time? Because after you've done, let's say 1,000 games or 1,000,000 games, you'll have explored a lot of states and you'll have to store for each state the probability of you winning at that point and all that. So how will that be different from exploring it again? Like,
why would if I know the probability of winning from there, why would I have to explore it again? Let's. I'm not even told you how you are going to solve it. Okay, let me explain that, and then you can come back and ask me these questions. Okay, if you still have them. Okay. Okay, great. So the way we are going to try and solve this game is as follows, right? For every board position, I'm going to try and estimate the reward I'll get if I start from there and play the game to the end. Right? Every board position, I'm going to look at the reward I'll get if I start from there and play till the end. Now, if you think about it, what will this reward connotate? Right? So, if I win from there, I'll get a 1. If I lose from there, or if I don't win from there, I'll get a 0. Right? When I say what is the reward I expect to get starting from this board position, right? It's essentially this average over multiple games. Some games I'll win, some games I will lose, or I'll not win. Right? Some games I win, some games I'll not win. So what will this expected reward represent after having played many games? The probability of winning, right? The reward is going to represent the probability of winning in this particular case, right? If the reward had not been 1, right? If it had been something else, if it had been +5, right? It would have been some function of the probability of winning, right? Or if it had been +1 for winning, -1 for losing, and 0 for draw, well, it's something more complex. It's no longer the probability of winning, right? It's the gain I expect to get, right? What fraction of games I expect to win over the fraction of games I expect to lose, or something like that, right? It becomes a little bit more complex. So there could be some interpretation for the value function, but in general it is just the expected reward that I am going to get starting from a particular board position. Okay, so that is what I am trying to estimate, right? Let us assume that I have such a expectation well defined for me, right? Let's say I have such an expectation well defined, right? Now I come to a specific position. Let us say I come to this position here, right? Let's say I come to this position. How will I decide what is the next move I have to make? Sorry? Whichever next state has the highest probability of winning. So I just look ahead to see, okay, where if I put the x here, right? If I put the x here, what is the probability of winning? If I put the x here, what is the probability of winning? If I put the x here, what is the probability of winning? Right? I do this for each one of these, right? And then I figure out whichever has the highest probability of winning, and I'll put the x there, right? So that's how I'm going to use this function. Does it make sense? Yes? It's very important. So this is something which you should understand. This is the crux of all reinforcement learning algorithms, right? I'm going to learn this function that tells me if you are in this state, right? If you play things out to the end, what will be the expected payoff that you will get, right? Whether the rewards or punishment or cost, whatever you want to call it, what is the expected value you are going to get? And when I want to behave according to this learned function, so when I come to a state, I look ahead, figure out which of the next states has the highest expectation, and then go to that state. Okay, great. How do I learn this expectation? What's the simplest way to learn the expectation?
Randomly selects to every time you come to that state, from that state, the fraction of games won.
It is essentially you keep track of what happens. Essentially, you keep track of the trajectory through the game tree, right? You play a game, you go all the way to the end, right? So you keep track of the trajectory, and if you win, right, you go back along the trajectory and update every state that you saw on the trajectory. You update the probability of winning, right? You just increase it a little bit. Or you come to the end of the game and you found that you have not won, right? You go back along the trajectory, decrease the probability of winning a little bit, right? Alternatively, you can keep the history of all the games you have played so far, right? After every game has been completed, you can go back and compute the average probability of winning across the entire history of all the games in which you saw that particular position, right? Make sense? That's the easiest way of estimating this probability, right? But the problem with this is A, you have to wait till the game ends, right? Or you have to store the history of all the games you have played, right? I mean, all of these could be potential drawbacks. Okay, you can get around the history part by coming up with an incremental rule, but the main difficulty here is you'll have to wait all the way to the end of the game, right, before you can change anything along the way. So tic-tac-toe is easy. It's like, how many moves can you make in tic-tac-toe at best? 4, right? The fifth one is determined for you, right? So it's basically 4 choices that you can make, right? That's easy enough to remember, right? You can always wait till the end of the game and then you can always make the updates, right? But what if it's a much more complex situation, right? What if you're playing chess? Maybe you can wait till the end. So what if you're cycling? Maybe you can wait till the end? Huh? Exactly. We don't know, right? It depends on where you're cycling. If you're cycling, learning to cycle in IIT Madras, it's fine. If you're learning to cycle somewhere on Sardar Patel Road, you don't want to even think about what end is there, right? So there are some tasks for which you really like to learn along the way, right? So this is where TD learning comes to help, right? I don't think I have that slide anyway, and I'm not using the fancy thing where I can draw on the projection. So let's see if I can do it here, right? Suppose I have come here, right? And from here I have played, at this point I know the probability of winning is say 0.4, right? So I came here by making a move from this position. So I said we were here, right? And we made we know that the probability of winning from here is say 0.3, right? But I made the move from here to come here, right? But here I had thought my probability of winning was, let us say 0.6, right? I thought my probability of winning was 0.6, right? But then I looked at my next states and I found that the best one was 0.3 somehow, right? So I went there, right? But now since the best I can do from here is 0.3, me saying 0.6 here, there is something wrong, right? So I should probably decrease the probability of winning from here. So why could it have happened that I thought that was 0.6 but the best among the next was 0.3?
Maybe the other branch that you had explored, the 0.4, that was fully explored and all of that was decreased to 0.4.
No. The thing is, so that whenever I came through this part, right, maybe I won before, right? It so happened that when I went through like this, right, initially I would have gone through like this and played the game. Right, the examples I drew, I might have actually won some of those games, right? So I would have changed this to 0.6, right? But it's possible for me to get here by playing a different sequence of moves also, right? So for example, to come here, right, I could have put the x first here and then here, or I could have put the x like I did here. I put the x first here and then here. Right? Either way, I could have reached this position, right? So there are many combinations in which I could have reached the same positions, right? Just to be nice to these guys, right? To reach here, there are different orders in which I could have put the zeros and the x's. Right? Here we are showing a specific order. The 0 was first put here, then put here. Right? The x was first put here, then put here. It could very well be I put the x first here and the o first here, and then I put the x here and the o here, right? There could have multiple ways in this thing was reached, right? So sometimes when I play those games, right, I lost, right? Sometimes when I play these games, I won. Therefore, it turns out that due to some random fluctuations, right? So sometimes I win when I go through this specific point, and therefore I have a higher evaluation of winning, right? But when I went through the other paths, I had a lower evaluation of winning. Right? But we know that really doesn't matter what path you went through in tic-tac-toe, right? Once you reach that point, right, what is going to happen further is determined only by that point, right? So what I can do now is take this 0.3, right, use it to update that 0.6 down. Down. So I'm very confident here. I think I'll win with the probability of 0.6. right? But the best probability I have from the next stage is 0.3. Therefore, here I should not be so confident, right?
How far down? Until 0.3 or?
Good point. That depends on how stochastic your game is, right? So if your game has a lot of variability, then you don't want to make a complete commitment to 0.3. So you might want to say, okay, no, let me move it a little bit towards 0.3, right? But if it's more or less a deterministic game, then you can say, okay, yeah, 0.3, yes, sure, let me go to all the way to 0.3. It depends on the.
Calling this a tree misleading.
Yeah, it's misleading. It's called game tree usually, but it's a game graph in this case. Yeah, yeah. Yeah. So is it clear? I mean, this is an instance of temporal difference learning. So how will I use the thing to update is this is called temporal difference learning. Okay. So there's one other thing which I should mention here, right? If I always take the move that which I think is the best move right now, right? Let's talk about it. I start tabula rasa. I have never played tic-tac-toe before, right? So I play the game. I play it once. I get to the end. I win. So now what I do, I go back, right? Whether I'm using temporal difference learning or waiting till the end, updating, whatever it is, I change the value of all the moves I have made in this particular game, right? So the next time I come to a board position, what am I going to do? I look at all possible outcomes. Everything except the one that I have played will have a 0, right? And the one that I have played will have something slightly higher than 0. I'm going to take that. Right? In fact, it will be like, how many of you watched the movie Groundhog Day? It will be like Groundhog Day. I'll be playing the same game again and again, because that's what happened to give me a win in the first time around, right? But that might not be the best way to play this, right? So I need to explore, right? So I need to explore multiple options, right? So I should not be always playing the best move, right? And I should not always be playing the best move. I need to do some amount of exploration so that I can figure out if there are better moves than what I think is currently the best move, right? So in tic-tac-toe, there is inherently some kind of noise if your opponent is random, right? But if your opponent is not random, and if your opponent is also playing a fixed rule, and if you are playing greedy, then you will be just playing a very, very small fraction of the game tree, and you wouldn't have explored the rest of the outcomes, right? So you have to do some amount of things at random so that you learn more about the game, right? So here is a question for you. When I am estimating these probabilities of winning, right, let us say I have reached here, I look down, right, and the action that gives me the highest probability of winning, say, gives me a probability of say 0.8, right, but I want to explore, right. So I take an action that gives me a probability say 0.4, okay. So I will go from here to another action that has a probability 0.4, right, another board position that has a probability of 0.4 of winning. So should I use this 0.4 to update this probability or not? No. Why?
You have to, because it's part of the learning experience.
Huh?
You haven't won or lost the game, probably. Wait.
Oh, that you are questioning the whole TD
You
idea.
have already won with that particular sequence, and now you're exploring it, so you shouldn't update it.
When you're exploring, you should probably wait for the end reward.
And or not just ignore the
Wait till end
exploration.
if it is possible.
Yeah. Okay. Any other answer?
You have to update it because you're learning that move. Whether it will be a good move or a bad move will be found out.
I have to update the value of that move. I agree. Do I update the value of winning from the previous board position was the question. So that 0.4 I will have to change, right? But do I change the 0.8? That was the question. The 0.8 was a probability of winning from here, right? I look or whatever was the probability. Let's say I had a probability of winning of 0.6 from here. I look at the bottom and the best probability of winning says 0.8. But then I take, because I am exploring, I take an action that has a probability of winning of 0.4. Right? The question is, do I go back and change the 0.6 towards 0.4, or do I leave the 0.6 as it is?
Unless this goes over 0.8.
Sorry?
Unless this probability of this current thing goes over 0.8.
that won't go, right? I'm exploring, right? I mean, this will be necessarily be less than 0.8. This will be 0.4. That will be 0.6. So the question here is, see, one way of arguing about this is to say that, hey, if I'm playing to win, right, I'll play the best action from here, right? And the best action says 0.8. Therefore, I should not penalize it for the bad action, which is 0.4, which I did to learn more about the system. Right? That's one way of thinking about it. Another way of arguing is to say that, hey, no, this is how I am actually behaving now, right? So I should give you the probability of winning about the current behavior policy, right? It should not be some other ideal policy. It should be about what I am behaving currently, and therefore I should update it, right? So which one is correct? First or the second? Questions. Yeah, but this is something. This is like I said, right? I'm going to ask you to think about the whole tic-tac-toe thing, and many of these answers have relevance later on. In fact, there are two different algorithms. One does option 1, one does option 2, right? So there's no right answer or wrong answer, right? Answer is? It depends. Yeah. So these are different things that you can think about in this. But now I told you about two different ways of learning with tic-tac-toe. One, wait till the end and figure out what the probabilities will be. The other one is keep adapting this as you go along, right? And both cases you'll have to explore. That's the tricky part here. In both cases you have to explore, otherwise you will not learn about the entire game. So this is where the explore exploit thingy comes in. Okay? Yeah.
So how do you know at what point to stop exploring and choosing the best?
Great question. Different algorithms deal with it different way. That's one of the crucial questions that you have to answer in RL. So it's called the explore exploit dilemma, right? So you have to explore to find out which is the best action, right? And you have to exploit whatever knowledge you have gathered, right? And you have to act according to the best observations already made, right? So this is called exploitation, right? So one of the key questions is, when do you know you have explored enough, right? Should I explore now or should I exploit now, right? This is called the explore exploit dilemma, right? And a slightly simpler version of reinforcement learning called the bandit problems. Okay, some colorfully called bandit problems. Yeah, of course, he's an expert on bandit problems. Yeah, you can. The bandit problems encapsulate this explore exploit dilemma. My God, a lot of people are turning and looking at you now, Shubho. But so this will ignore a whole bunch of other things like the delayed rewards, the sequential decisions and other things. Even in the absence of all of these other complications, right? Even if I say that all your problem is you have to take an action and you will get a reward. Okay, your goal is to pick the action that gives the highest reward. I'll give you 10 actions. You have to pick the action that gives you the highest reward, right? But the problem is, you don't know what is the probability distribution from which these rewards are coming, right? So you will have to do some exploration. I have to actually do every action at least once, okay, to know what will be the reward, even if they are deterministic, right? So I can't say which is the best action before I try every action at least once. If it is deterministic, it's fine. I can just try every action once and I know what is the payoff, right? But if it is stochastic, I have to try every action multiple times, right? How many times do you have to try it depends on the variability of the distribution.